So from the previous formula, which is U equals to M, changing H or T?
Changing temperature.
Changing temperature. Okay, so from the question, they gave us mass already, and they gave us specific heat. So we're just supposed to find the change in temperature. We saw that initially it was 94, and we found 5. So we just take 5, change in temperature will be 5 minus 94, which will be given to -8. So just substitute our formula, it will be equals to 869. Specific heat. So you can calculate this. Calculate it. Just calculate.
So basically here, usually this, okay, you can just minus 1.
Negative is 9.
Okay, it's okay, it's okay now. Yeah, okay, yeah, thank you, yeah. So we can say, so basically we can use this equation to calculate the heat released. So and here the M is the mass. So the mass, we have the mass number, right? And also the here S is the specific heat. Okay, and the change and the temperature change with this number. Okay, finally we get this.
Well, because of the temperature change, why did you just do 94 minus 5?
In the final, the temperature should be in the final, yeah, final, because here, the final temperature minus the initial. So here is minus 5. So the whole number, the answer is minus. So what does this mean? The system loses or gains energy. Gains? Loses, yes. Yes, when the temperature changes from 94 to 50, of course, the system loses energy. Okay?
Understand the question. Oh, yeah.
So here, you can see this is temperature changes, and the number is minus, which means the system loses energy. Okay. So here's another question, okay? So do you know how to cut the steel? So basically we also use give energy or like a fire, but also here of course it's not fire. You can also use fire, okay?
I've done it before.
Oh really? So you know how to do it, right? Okay. So if fire is very high, the temperature of fire is very high, right? So they know what temperature.
I didn't use fire, I used the grind.
Using, I mean, for example, here the temperature is like 1,535 degrees, okay? The temperature. And of course, finally, it will change to the room temperature, this. And if the cut, when we cut the steel, the mass of the steel is this. So now the question is, how many energy it needs to cut the steel? How many energy? So yeah, here you can use the same equation, okay? Also you can use this equation. So in this equation, just the area, we know the specific, the mass, we know the mass, right? And the temperature. Ooh. Okay. Yeah, hurry up. It's very simple.
fine.
Where are you going?
I have a question.
You said
It's understanding.
okay.
Yeah, we don't understand.
Okay, I'll explain it. So yeah, you get that. So what I did is like the formula is Q equal to MC times Q is the heat unit, right? M mass C is this unit, the specific constant, yeah, and change this one is changing temperature. So for me, I just expand this change temperature to TF minus TI. Then I just put everything.
But we have Q again on the right side of the equation.
Q again.
Yeah, like that one is Q is equal to MC
Oh.
T. Then we would Q again.
Yeah.
So that's the panic we are facing.
Dennis is happy.
Okay.
Yeah. So
Okay. Yeah. Good. Okay. Yeah. Thank you.
So what you did was correct.
Ah,
That's
okay.
wrong equation.
Can you repeat it? I didn't understand. Please.
she'll explain.
No, you. Yeah, you don't. And go slow.
Okay.
Yeah.
Yeah. The formula is Q is equal to MS changing
What
temperature.
is Q?
Q is heat.
Which kind of it?
It's depending on the
What?
Okay, it's Q is heat.
what?
Q is heat, right?
Q is
Yeah.
okay. Continue.
Okay. M is mass.
Yes.
S is mass of the substance. So for this question, it should be it's iron. Yeah. S, that's specific heat constant.
What about C?
Huh?
Yeah, why did the C come from?
Oh, yeah, the same C and S, because this is just it's like an expression. Yeah.
So using the B.
Yeah, for the other book there is C and the other book is S. So it's depending on which book I use.
You study as
Okay.
Yeah, of course, because
You see, in your formula you wrote final temperature minus initial, but in calculation you wrote initial temperature minus final.
who told you? Final. You see now, okay.
Anyway.
In fact,
now come in the value.
in fact, you know what? He wrote 153.
Yeah, he needs 1.5. Okay, it's okay. So yeah, basically we can use this thing. Okay. So we need to provide this energy to the system. Okay. So the system will gain this energy and then it's produced. Okay. Now we introduce the third part of this chapter. It's about standard enthalpy of formation and the standard enthalpy of reaction. So because there is no way to measure the absolute value of the enthalpy of a substance, so must I measure the enthalpy change for every reaction of interest. So basically, we can use like a standard enthalpy of formation of substance to calculate, to do more calculations. So what is the standard enthalpy of formation of the substance? So the standard enthalpy of formation is a heat change that results when 1 mole of a compound is formed from its elements at a pressure of 1 atom. So here, compound elements. So what's compound? Remember? Compound means substance with more than one element, right? So this is compound. So basically, so for a compound, it's made by different elements. So the stand and enthalpy of formation of a compound is the heat change. So when one mole of a compound is formed from its elements. Okay. For example, water. Water has two elements. One is hydrogen, right? Another is oxygen. So how to call the standard enthalpy of formation of water? So we just use this reaction. Okay, after this reaction, this heat is the formation, is the standard enthalpy of formation of water, of gaseous water. So this level can be obtained from experiment. Okay. So we can design this experiment, and then we can measure the heat change. Okay. And this heat change is the standard enthalpy of formation of this compound. And the standard enthalpy of formation of any element here, of any element in its most stable form is 0. We just put the standard enthalpy of formation of any element is most stable is 0. For example, oxygen. For this oxygen, its most stable is O2, right? O2 gases. O2 gases is very stable, right? So the O2 gases, its standard enthalpy of formation is 0. And the O3 has more energy than O2. And the number is 142. Okay. And for the carbon, the most stable state is graphite. The graphite is the most stable. So this is 0. But the diamond, when the diamond is formed, of course, it's stable. But the energy of diamond is higher than the energy of graphite. We can basically the diamonds are formed by the nature, in the nature, right? But also we can man-made diamond. How to do? Just using the graphite and the high temperature and high pressure. So the graphite can be changed to diamond. So the diamond carbon has higher energy than graphite. So for carbon, for this element, the graphite carbon is 0. Okay, so this is about the standard enthalpy of the formation of any element in its most stable form. We set is like 0. Okay, here is a table of the standard enthalpies of formation of some compounds and elements. So we can say, for example, this element. So this is stable. Is the most stable state is 0. Okay, and this element is 0. We can say bromine. Okay, is 0. This is 0, but this is not 0. Okay? Both of them are only made by carbon, but they have different energy. This is the most stable state is 0. Okay? So for example, in the most stable state is 0. Chloride, okay? And then and the fluoride. Gaseous fluorine is 0. Okay? Hydrogen. But H2 is stable, is very stable, right? But single hydrogen is not stable. It's not the most stable, right? So it has energy. It has energy. But H2 is stable. So for element, we can say 0. And for compound, so we can use this kind of reaction, design this kind of reaction to measure the standard enthalpy of formation of a compound. So this sample, for example, these samples, okay, are obtained from experiments. Okay. Like the oxygen. Oxygen can have 3 states. Single oxygen, 2 oxygen atoms. This guy has 3 oxygen atoms. But only this one is, among these 3 stations, this one is the most stable. So we set its energy enthalpy of formation is 0. But other has some numbers, okay, has high energy. And we also can see like NO, right? But all this is a compound. This is compound. All of them have some. If a compound, definitely they should have some enthalpy, have some number of the enthalpy of formation. Okay, but for the elements, so some has some, but only one doesn't have. Okay. So we can find the standard enthalpy of formation of all substances from book. Okay, this is just one table. Okay, you can find standard enthalpy of formation of other substances. Some are 0, some are obtained from experiments. Okay. After we know the standard enthalpy of reaction, after the formation of substance, we can calculate the standard enthalpy of reaction. For example, for this reaction, the standard enthalpy of reaction is equal to the sum of the products minus the sum of reactants. Okay. And then we can get the standard enthalpy of reaction. And we will also, so here to show how to use the enthalpies of formation of substance to calculate the standard reaction enthalpies. If the enthalpy of reactants is here, and the products is here. So we can say there are some difference between them. So this difference is the enthalpy of reaction. Okay. So in this case, we can say the enthalpy of products. The enthalpies of products are lower than those of reactants, right? So after this reaction, the system will lose energy or gain or gas energy. will lose or gains? Lose, yes. Why?
To change to chemical energy.
Yeah, because the energy like energy of products is lower than those of reactants. So the system will lose. If the system lose energy, so this means after the reaction, so the action will release energy, right? Okay. So question. So benzene burns in air to produce carbon dioxide and liquid water. How much heat is released per mole of benzene combusted? We know this is the reaction. It is balanced. Okay, and here to tell you the standard enthalpy of formation of benzene of this guy. Okay, is this number. For others, we can find from this table, right? So how to use the standard enthalpy of formation of substance to calculate the standard enthalpy of reaction. So use this one, right? Use this equation. So this number for the reaction is equal to products minus the reactants. Okay. Your turn.
I'm not so sure on that one.
Think about it.
Yeah, go back to him.
Use the equation, right? Products minus the reactants. Okay? Now, this is products. This is the reactants.
Yeah, the question on that one, go back.
And the question on top.
Go back
Oh,
to
here.
the previous.
The question is here.
Go
So
back to
what-
the previous slide.
What? That-
Yes,
The formula.
Yeah, on the formula here. Now the last one. Sum of n. What is n?
Which one? Which?
This is a summation of n.
And?
On the products, yeah.
And
So n and m.
Oh.
Like what's the
here's a C. Basically, here is n is depends. For example, basically, it's not n. It's like A, B, C, D, right? So basically, use this equation. Okay, this equation. So here is coefficient number. We usually think about coefficient number.
Go and try.
Yeah, I'm thinking about it. Wait.
You don't here just like the sum of the products. So just using the n. Okay, n is include the formation C and D.
Just add the two.
Okay, so you just use this equation.
Don't analyze this.
C D. Okay, A B, and then here the number the coefficient number is A B C D. So here should be A B C D. Okay.
Yeah. Go and try.
Yeah, should work.
So smart.
Use the down one.
Which one? Oh, the down one.
No, yeah, the down one.
Which down one?
What are you talking about?
I didn't see it.
Well, he is smart. He is very smart.
Okay.
Like,
Where's the table again?
on your own.
The number is here. So maybe you use black or with a pen? No.
Here.
Monitor.
Are you sure it's a whiteboard, that one?
Yeah, it's right. Okay.
And they can give you
What is?
a permanent one. If you don't have the screen, guys.
You can write over there.
Okay.
Well, wait.
Yeah, because you need this table.
What's that formula again?
Formation.
Yeah,
So here is carbon CO2. Where's CO2? Yeah. This is also the state, the gas, right? Which one? Yes. Yes. Okay.
Okay.
Carboxylable.
A negative looks fine.
Oxygen 0. Then this
Water.
Natural.
same one. Then water.
Water is they are liquid or gases. Liquid, yes.
Oh man. Not again.
Okay. Can you please go back to the previous slide? You see a formula. Okay. Are you okay? Are you good?
That's
so this is-
this equation.
Yeah, yeah.
Yeah,
So these are the products, and then these are the reactants, right?
Yeah.
Okay, C.
Coefficient.
Coefficient of
This
displacement.
knows what is good.
12. Multiplied by
Yeah.
for C, we found it's this, right? Okay, go back to the formula.
Same thing for D.
Yeah.
Okay, the complicated, right?
It's a lot of shit.
Okay.
Yeah, yeah.
6 times H2.
6 times H2O liquid, which is negative 285.
Okay, good.
Then minus the same thing for the other part.
Yeah. What's the coefficient?
Reactants.
2 times.
Okay, now benzene, we here, we do benzene is one. Benzene. Benzene. You can find benzene here, okay? Yeah. Okay.
Oxygen. What do you find for oxygen?
So this is stable. This is the most stable
Okay,
state.
most
right?
stable is
It's
zero. Okay.
Okay, yes. Good.
Can someone calculate? What's the calculator?
Use your head, Dixon.
Use yours.
That shit.
Okay, I think it's okay now.
You're back in.
Yeah, okay, thank you. Yeah, can you just explain
Okay.
to others?
Great.
Who didn't understand?
Me. Everyone.
Interesting. I thought so. Okay, so we've been given this the standard method of the formation of benzene. It's here because you can find it here, first of all. You have to know that. And the question states benzene air to produce carbon dioxide and liquid water. Question is how much heat is released per mole of benzene combustion? So you must know the formula first of all. If you don't know, you're on.
Like you were, right?
No? So you have to check on this table to get the values. So for the first one, benzene has been given. Oxygen is the most pure form, so it's 0, it's stable. So it's stable. You come to carbon dioxide. So you have to check the state. So if you know it's gas, you come here and check, find it here, write it down somewhere. For water as well, you check the state. It's liquid here, yeah, you check it, write somewhere. Then you just replace in the formula.
Okay. Good. Okay, yes, thank you.
You're welcome.
Panic you.
You ran away.
Did I?
Coward.
Did I? Oh, you didn't choose that one. Use the other one. No, the other one.
Ooh.
Like panic. Words. Go fix it. So that was there's no one to do.
Down there.
Anyway.
Okay, so, yeah. So basically, when we calculate the standard level of reactions, we can use the sum of the products minus sum of the reactants, they are formations. Okay, and so you can start the coefficients. There's 12 and 6. Because the unit of the formation of the standard enthalpy of formation is per mole, is 1 mole, okay? But here it's 12 mole. There is 12 mole, so you must multiply by the 12, and this guy should become the 6, okay? And here it should be 2 here, and this is 0, the most standard state. And then you can find this sample from the table, and finally to get the standard enthalpy of the reaction. Okay, so any question for this? Okay. And finally, okay, so now we introduce the enthalpy of solution. So the enthalpy of solution is the heat generated absorbed when a certain amount of solute dissolves in a certain amount of solvent. So basically, when the substance dissolved in solution, in solvent, sometimes they release energy, sometimes they absorb energy. So why someone's absorb, someone's release? This is because basically for when it is solid, in the solid, for example, the crystal. When the solid, when the crystal, we broke the crystal, right? They dissolve in solution like which broke the crystal structure. So in this the first process. This is the first process. The first process will absorb or release energy. How do you think about this process? It will require energy or it will release energy. When we when the structure, crystal structure is broken and dissolved in solution, this process leads energy or release energy. Absorb, yes. Okay, so the first step. Second step, when it broke and be changed to single iron in the solution, and it will, we introduced it will surrounded by the solvent molecules, right? Like water, the water molecule will surround it. It looks like it reacts with water to form the formation surrounded by water. So in this process, it will release energy or absorb energy. Yes, it will release energy. So basically, the first step will absorb energy. The second step will release energy. So this is why, if the energy of the first step is larger than the second one, so this means it will absorb energy or release energy. So if the first step, for the first step it absorb energy, right? If the first step, the energy in the first step is higher than the second step, so the whole process will absorb energy. If the second step will release energy. If the energy released is more than that of absorbed, so the whole process will release energy. So this is why some substance release energy, but some substance will absorb energy when they dissolve in solvent. So this, for example, this is the enthalpy of solution for different compounds, for different amounts. Because the first two are negative, okay, and the others are positive. So for this, the number is negative. What does it mean? Absorb or release? Release. Why? Because it's minus, right? Minus means the system lose energy. Okay? The system lose energy means it release energy. Okay? And this is positive, so they need energy. So for example, sodium chloride, we all know this, right? So if we dissolve the sodium chloride in the water, which way can speed the process? Heat or cool? Heat. Why? Yes, because it leads energy. So when we provide energy, we can speed the process. Okay, this will release energy. Now question, which substance could be used for melting ice? Oil, gas. No, I think you are more close to your turn. This to release energy. This for absorb energy. So which one is better to melt ice? Melt ice means we hope is release energy or absorb energy. Absorb energy? Melt, we want to melt ice. Yes, release.
What's the energy in this case?
Yes, good. Yeah, the answer is the first two can be used for to melt as ice. Yeah, because when it is dissolved in water, it can release energy. And of course, it releases energy and it's better to melt ice. Because when the ice melts, it needs energy, right? So we hope that the process release energy.
But in this case, the ice, yes, it's frozen, it's ice. Do you think they need heat for it to melt?
Yeah, but where the heat come from? Should come from the process, right?
Yeah.
So the process should release energy. With the solid dissolved in water, it can release energy. And it release energy, this energy can be used to melt ice. Okay? Have a short break.
Okay.